So unfortunately, I'm not able to be with you in class today. However, we do still need to continue talking a little bit about asymptotes and limits and how those are related. If you think back to what we learned on Friday, we learned about how horizontal asymptotes were related to limits. And we said that if we look at the limit as x approaches infinity, I'm just going to flip back. If we look at the limit as x approaches infinity or x approaches negative infinity, those two limits will help determine whether we have a horizontal asymptote or not. And we can use some of the same techniques that we used to find horizontal asymptotes to find these limits. Today we're going to be looking at how limits and vertical asymptotes sort of go together and how they impact one another. So let's start with reminding ourselves all about vertical asymptotes. When a function is rational, in other words, when it is a fraction, it is very likely that the function will have a vertical asymptote. If I ever want to figure out where those asymptotes are, my first step is to factor. For this particular function, the numerator would factor to be x plus 3 times x minus 3, and the denominator would factor to be x plus 7 times x minus 3. When I see that the x minus 3's cancel, I remember that that means that there's actually a hole in the graph at x equals 3. And I realize that that means that the only vertical asymptote would be at x equals negative 7. Since a function cannot cross through a vertical asymptote, so if you look at a graph, it can't ever cross through, it forces the y values of that function to either go up to positive infinity or down to negative infinity. So let's take a look at a graph that has one of these asymptotes and see how that impacts the graph and the limits. If we look at this graph, there are two different vertical asymptotes. There's the asymptote at negative 2, 1, 2. There's also the vertical asymptote at positive 2, 1, 2. If I look at the limit as x approaches negative 2 from the left side, so if I'm starting on the left side of the graph and I'm going towards that from the left side, we can see that the y values of the graph sort of skyrocket. They shoot upwards. When that happens, we say that the limit approaches positive infinity. When we look at the limit as x approaches negative 2 from the right side, you can see that the limits skyrocket downwards. They sort of sink down. So the y values going down like that means that the limit would be negative infinity. Since those two limits are not the same, since one of them is a positive infinity and one of them is a negative infinity, we would say that the overall limit as x approaches negative 2 does not exist. So the big question becomes, how do we do this without a graph? Just like on Friday, we started by saying, okay, here's what we kind of know. Here's what a graph would look like. The question becomes, how do we do this algebraically? How do we handle finding these types of limits if we don't have a graph in front of us? The first thing we need to determine is how we know whether to even be worried about these types of limits. So, how do we know when we should worry about vertical asymptotes happening? Whenever you see a fraction, or a rational function, that's another word for fraction, you should definitely start thinking about, there's going to be a vertical asymptote here. For example, if f of x was this function, what x value would make us think about vertical asymptotes? What I'm going to look at is the denominator here. Whenever the denominator equals 0, I know that a vertical asymptote is something that I should worry about. So in this case, I would say when x equals 2, I should be worried about a vertical asymptote. So how do we actually figure out the answer? We have to sort of use our imagination. So just like on Friday, we had to sort of imagine what happened when you plugged in an infinity, because you can't really do that. We have to sort of imagine what's happening here. Let's say that I wanted to find the limit as x approaches 2 of that same f of x function. I know from my previous experience with limits that that means I need to examine both sides. So automatically I need to think first, look at the limit as x approaches 2 from the left of that function, and then look at the limit as x approaches 2 from the right of that function and see if they match. So let's practice doing that. Now we know we can't actually plug a 2 into here, so we have to kind of use our imagination. Pick a number that is close to 2, but slightly to the left of there. So if you think about a number line, if this is the 2, you want to pick a number right there. I usually think about that number as being kind of like 1.99999. So if I imagine plugging that number into here, because it's very close to 2, the answer to the bottom, that number minus 2, would be a very small number. It would be like 0.00001. So if we have 3 divided by a very small but negative number, we have to figure out what's going to happen. If you have 3 pizzas and you want to cut them into very, very, very small pieces, you can make a lot of pieces. So the answer here would be really big, like infinity. Now let's say we take a number slightly to the right of the positive 2, like 2.0001. If we do 3 on the top and we plug in like 2.00001, since it's slightly bigger than 2, it would still be very small, but it would be positive. And if we do 3 divided by a very small positive number, we get a very big positive number. Now, since these two values do not match, we would say that our overall limit here would be DNE. All right, now I know this is weird to think about. I know it's weird to think about being close but not exactly being equal, so we're going to do a bunch of examples here. So let's look at the bottom. First, we're going to practice doing this by looking at a graph. So we're going to look at a graph on our calculator and see if we can figure out these limits. On our graphing calculator, first I'm going to graph 1 divided by parentheses x minus 4. Now you don't necessarily have to graph this yourself. I'm just going to show you the picture. I'm going to zoom 6. Immediately upon seeing that I'm looking at the limit as x approaches 4, I should think to myself, ooh, something weird is happening here, because I know there's going to be some sort of a vertical asymptote at that specific number. So, looking on this graph, I can see that there's something weird happening right here, right close to the 4, which is what I expected. As I approach this asymptote from the positive side, I can see that my values sort of skyrocket up. So I would say that the answer to this question is a positive infinity. Now look at number 2. Let's look at the same function, but look at the values as we get close from the left side. From the left side, they sort of sink down really fast. So the answer would be negative infinity. Now we're going to do the same process, but we're going to do that with a slightly different function. So I'm going to change this to x minus 2 squared, which is my new function right here. I'm going to look at the graph. I can see while that's loading that I'm looking at the numbers that are close to 2, and that should make me think, ooh, we're in vertical asymptote territory here because 2 causes a problem in this function. All right, well, if I look at this graph, as I approach 2 from the right, the values skyrocket. So since they go up, I would say that my answer is infinity. Now, if I approach 2 from the left, they also go up. So again, I would say that my answer is infinity. In this case, if you were asked about the limit as x approaches 2, of 1 over x minus 2 squared, you would actually say that your answer is infinity. Sorry, I wrote that off to the side a little bit. You would actually say that your answer is infinity, and the reason is because these two limits that we just found, they matched. All right, we're going to go ahead and we're going to look at the next page. I'm trying to angle this camera so you guys can actually see what I'm doing all at once. Here we go. We're going to go ahead and look at the next page. Calculate the values of these limits without looking at a graph. We're going to save, by the way, those last two problems, problems 5 and 6 at the bottom of that page, just in case you guys have questions when I see you later on this week. So we're saving those for later. Without looking at the graph, we need to kind of use our imagination. So in this problem, I can see it's a fraction. That immediately makes me think vertical asymptote. I know I want to plug in 3, but I can't. So I want to plug in a number that's close to 3, but slightly on the positive side. So if you think about a number line, if 3 is right here, this would be like 3.0001. If I plug that number in, 3.00001 minus 3 would be very small, but it would be very small and positive, which means my answer would be very large and positive. If I do the same problem, but I choose numbers that are approaching from the left side, then if you imagine a number line, a number that's slightly to the left of 3 would be like 2.9999. So if I plug that in, this time 2.99999 minus 3 would be very small, but negative. So I would have 1 divided by a very small negative number, which means my answer would be negative infinity. Now for problem 3, you can see that I put that problem as the third one because it's connected to the first two. If one of my answers from the right is a positive number and from the left is a negative number, we would say that our overall limit does not exist. Let's try the same thing, but let's look at a function that operates slightly differently. In this problem, I can see that it's a fraction. That should immediately make me think, ooh, there's going to be a vertical asymptote somewhere. And specifically in this problem, it would be at the 4, which of course is the number we're being asked to evaluate, because of course it is. If we choose a number slightly to the right of a positive 4, that would be like 4.0001. Now if we plug that in there, 4.0001 minus 4 is a very small number, and it's positive. So we would have 3 divided by a very small positive number squared, which stays positive. So my answer would still be infinity. Now in this problem, let's do the same thing on the other side. So if we pick a number slightly to the left, that would be like 3.9999. If I plug that in, it's very small, but it's negative. Now, unlike in problem 2, where it stayed negative and small, because this one is negative and small, but we're squaring it, it becomes a positive. So your answer would be positive infinity, which means because these actually match this time, the overall limit would actually be positive infinity. Now, all we're going to do in these questions is do the exact same thing. We're going to incorporate problems that have fractions in them. Therefore, we are worried about vertical asymptotes, but we're doing it in the context of a piecewise function. So, let's say I ask you to evaluate the limit as x approaches negative 2 of f of x. Right away, I notice that negative 2 is one of the border numbers here. The top function is controlling the numbers to the left of the negative 2, and the middle function is controlling the numbers to the right of the negative 2. So in order to figure out this limit, first I need to find the limit as x approaches negative 2 from the left, and then I need to find the limit as x approaches negative 2 from the right and see if they match. From the left means look at the top function. Can you plug in a negative 2 here? No, it's a fraction. It causes an asymptote. But pick a number slightly to the left of negative 2, maybe like 1.999. Left of negative 2 would be like negative 2.001. Negative 2.001 plus 2 is a very small number, but it's negative. So we would have 1 divided by a negative small number, which would be negative infinity. Now, if we plug in negative 2 slightly to the right, we're looking at plugging negative 2 into the middle function, which would be 4 minus 5, which is negative 1. Since these do not match, my answer here would be DNE. Now let's look at the limit as x approaches 0. In this problem, 0 is not a boundary point. The number 0 for x lies entirely within this region. 0 lives here only. So I ask myself, can I plug it in? Because the number one rule of limits is if you can plug it in, then to find the limit, you do plug it in. If I plug in 0, I get 0 minus 5, which is negative 5. I don't need to check both sides because the 0 is entirely within that zone. So he controls both sides. We're going to save number 2 for when I see you again, and then we can go over it if you're having any trouble. Tomorrow in class, you're going to be doing a review. Now, I want to be very specific about this. The review tomorrow, I want you to skip problems 17 and 18. It's on pages 22 to 27 of your packet. I want you to do everything except 17 and 18. On Wednesday, when I see you again, we will go over any questions that you had from the review, any questions that you had from this homework assignment that you're going to do tonight. And then we will do an activity to help us learn how to practice 17 and 18. That night for homework, you will do these 2 problems and these other practice problems, as well as look over the rest of your review. And our big quizzes are on Thursday and Friday. I will see you tomorrow, and have a great day.